So Bernoulli's equation actually comes from Euler's equation. So the first thing you want to do is to derive Bernoulli's equation. Doing that using Euler's equation along a streamline. So I'm going to take Euler's equation, apply it along some streamline in some direction s, and then when I do that, I'm going to make some assumptions. First one is that I only consider the tangential acceleration, so I only care about the acceleration along that streamline. I don't care too much about the centripetal acceleration, assuming my direction is not changing too much. In other words, the radius of curvature is fairly large here. Second assumption is that it's steady flow, so no change in time or no local acceleration. And then the last one is that the fluid is incompressible, so that the density I can treat as a constant. So beginning with Euler's equation from the last lesson, negative partial derivative d by dl p plus gamma z is rho times acceleration in that L direction. Now to apply this along a streamline, all I'm really doing is changing the L to an S. So along my streamline is my S coordinate, so that goes where the L is. So minus d by ds, p plus gamma z is rho as, so again in this streamwise direction. And then we know from the acceleration lesson that acceleration is this local part, dv dt, convective part, dv ds, goes in the tangential direction, and the centripetal part, v squared over r in the normal direction. But I'm going to be making my two assumptions. First assumption that I only care about the tangential acceleration, so 0 centripetal acceleration, so I don't need that guy. And then my second assumption was that this is steady, so if this is steady, I get 0 local acceleration, so that guy's gone. So all I'm left with for my acceleration in the streamwise direction is this convective term, v dv ds, and then that's implied to be in the tangential direction, so I don't need to worry about that too much. I only care about this part of it. And then now, because I'm also assuming the flow is steady, there's no dependence on time, so generally v is a function of time and space, t and s. Because it's only s, I've assumed t is gone, I can change these partial derivatives into full derivatives. And then plugging this back into Euler's equation, same thing here, no function of time, so I can change that to a full derivative, minus d by ds, p plus gamma z, rho, and then there's my acceleration, dv ds. And now what I want to do is actually get these derivatives together, but to get these derivatives together, I need this derivative to come out front, so I'm going to use a little trick. And so that trick is based that v dv ds is the same thing as the derivative of this whole quantity, 1/2 velocity squared. It's a little hard to see where that comes from, but if you go the other way, in other words, take the derivative of this function, derivative of v squared is 2 comes out, cancels the half, I'm left with a v, but then because v is a function of s, on chain rule, I need a dv ds, so what I'm left with over here is a v dv ds, which is exactly what I started with. So you can see, going backwards, this is true, so going forwards has to be true as well. And so now this is going to replace this term up here, and again, I've assumed that the density is constant, so I can also throw the density into this derivative without any problems. So plugging that into Euler's equation, minus d by ds, p plus gamma z, then in the right-hand side, here's my new acceleration, 1/2 rho v squared, derivative of that. Now I combine these two derivatives, so basically move this whole thing to that side, put it inside the derivative, so 0 is the derivative of p plus gamma z plus 1/2 rho v squared. Then integrate that, so left-hand side integration, derivative goes away, I'm left with the inside, p plus gamma z plus 1/2 rho v squared. Left-hand side, integrate 0, you get a constant, so p plus gamma z plus 1/2 rho v squared equals constant. This is Bernoulli's equation. It can also be written in this form, p1 plus gamma z1 plus 1/2 rho v1 squared is equal to same thing at a different point. So essentially I'm taking some point, 0.1 along a streamline, calculating this, setting it equal to another point along the streamline. Technically, this equation, Bernoulli's equation, is only valid along a streamline because that's how we derived it from Euler's equation. I want to talk about a few consequences of Bernoulli's equation. We have pressure, we have some height, we have velocity. All these things are interrelated to leave us with the constant, so if one goes down, one of the other two things has to go up, or maybe both of them. If we're dealing with a horizontal flow, So a lot of times if you're driving your car or if you're flying in a plane without any change in elevation, this is the situation that's happening. And in that situation, so again, if I can ignore any change in height, so z is going to be the same, then the only two things that can change are pressure and velocity. And we can see that if those things are constant, if one of those goes up, the other one has to go down. So if pressure goes up, velocity has to go down, or vice versa. If my velocity goes up, my pressure goes down. Now it might seem a bit backwards because you can always think of a high velocity having a higher pressure. If you stick your hand out your car window at 20 miles an hour, you don't feel as much pressure as if you stick your hand out the window at 60 miles an hour. So how does this make sense? So what's happening in this situation is that you have some airflow around your hand that's showing whatever speed you're going. You're just going to call that V0. So if you're going 20 miles an hour, your velocity V0 is 20. Then you stick your hand out the window, what happens as the air comes in, your hand is actually stopping the air. So the velocity right at your hand goes down to 0. And so what you're really feeling is this change in pressure from the velocity out here, or the pressure out here, to the velocity in here. Now the velocity out here is 20 miles an hour. That is a low pressure. Velocity equals 0 is your high pressure. You feel that change in pressure. But if your velocity up here is 60 miles an hour, that's an even lower pressure. So when you get up to 0, that's a bigger pressure change. So again, you're measuring that pressure change. And the fact that as pressure goes up, velocity goes down and vice versa, that's actually the reason why planes fly. So if you take an airfoil, basically the wing of a plane, this thing is designed to make the velocity on this side go faster than the velocity on that side. So it has some initial velocity up here, velocity on top is going faster, velocity on the bottom is going slower. Slower velocity means higher pressure. So I have a higher pressure on the bottom than I have on the top, so more force pushing up and pushing down. That's going to give you a lift force, and that's basically how planes fly. So first example, using Bernoulli's equation, a very similar scenario to what I just described with a airplane wing, flow going around it horizontally. And so have upstream velocity, 80 meters per second, that's basically how fast the plane's flying. Then I measure the flow at the top of the wing to be 85 meters per second, flow at the bottom of the wing, 0.2, 75 meters per second. So again, this wing's been designed so that the air over the top flows faster than the bottom, so it's going to give me some lift to be able to fly my airplane. I want to know what the pressure difference is between points 1 and 2. So essentially I can relate this pressure difference to a force, because force is pressure times area. So with this pressure difference, I can figure out what sort of lift force I'm generating with my wing. So I'd love to just write down Bernoulli's equation for this scenario. P1 plus gamma Z1, 1/2 rho B1 squared, is P2 plus gamma Z2 plus 1/2 rho B2 squared, and compare these 2 points, points 1 and point 2. But I can't actually do that. You know why? If you look at my picture up here, it's pretty clear that some of this air is going to go over top of it, some of it's going to go below it. Air cannot go both above it and below it at the same time. So what that means is that point 1 and point 2 are not on the same streamline. So if they're not on the same streamline, I can't actually use Bernoulli's equation officially, because Bernoulli's equation was derived for 2 points being on the same streamline. So the question now is, what should we do now? So what I can do is look at the streamlines way up here. So point 1 is going to start from some streamline way up here. Point 2 is going to start from some streamline way up here. So I can compare both of those points to some upstream conditions, some velocity V0, some pressure P0. So I can write down for point 1, Bernoulli's equation for point 1, and it's 0.0 aversion. Same thing for point 2. So I have all the pressure, C, velocity for point 2, and then it's way up here values as well. And then if I assume that gamma delta Z is small, so essentially, remember from the hydrostatic pressure lesson, if I'm going up in air or any gas, any light fluid, any change in height, unless it's a really, really, really big change in height, it's not going to affect the pressure or velocity that much. So the gamma is delta Z, the change in distance between point 1 and point 2, or change in distance between point 1 and the upstream point, is relatively small. Thickness of wings is not very big, So I'm going to assume that my gamma delta Z is small. So essentially, gamma Z1 and gamma Z01 are the same thing. So cross those out. Similarly for this equation, gamma Z2, gamma Z02 are basically the same thing. Let's cross those guys out. And then in terms of my upstream conditions, up here I have velocity V0, pressure P0. Doesn't really matter where I am, doesn't matter what streamline I'm on. They all have the same velocity and pressure. So what I can do now is basically take away these second subscripts. So instead of P01, I just have PO. Instead of P02, I just have PO. Instead of V01, it's just VO. Instead of VO2, it's just VO. So now what I have, the right-hand side, P0 plus 1/2 rho V0 squared for both of them. If these two are the same, that means that these two are the same. So essentially what I'm left with is P1 plus 1/2 rho V1 squared plus P2 plus 1/2 rho V2 squared. And this is actually the exact same equation I tried to write in the first place but couldn't because they're born in the same streamline. Again, they have z's in them, but I'd still cancel the z's the same way I did here. So technically, I could have just started with that equation, ended up the same point I'm at now. So even though technically Bernoulli's equation only works for 2 points on the same streamline, there's a lot of situations where it works no matter where you are. Generally, if the fluid is irrotational, that's one of those cases, and this is a situation where that happens. So technically here, I could use any 2 points I want, don't need to be on the same streamline. I can write down Bernoulli's equation for those 2 points. So now finishing off that example, I can rearrange the equation I just had. So move the P1 to this side, move the V2 to that side. So pressure difference, what I'm looking for, P2 minus P1 is 1/2 rho V1 squared minus 1/2 rho V2 squared. We're just pulling the 1/2 rho out. 1/2 rho, parentheses V1 squared minus V2 squared. So just plug the numbers in. 1/2 density of air. I'm assuming STP, even though the question didn't say that specifically. You can assume that. It's 1.2 kilograms per cubic meter. Then my velocity is 85 meters per second, square that, minus 75 meters per second, square that, gives me a total of 1,024 pascals as the pressure difference. So next example, I have a cup 30 centimeters tall, completely filled with water. I then come along and I punch a hole in the side of my cup, halfway up at 15 centimeters, and I want to know how fast is water going to come out of that hole. So to find the answer to this, you're going to use Bernoulli's equation. P1 plus gamma Z1 plus 1/2 rho V1 squared is P2 plus gamma Z2 plus 1/2 rho V2 squared. Obvious question now is what should we choose for points 1 and 2? I can pick whatever 2 points I want. So what 2 points should I pick? General answer to that question is want to pick points either where I'm trying to find something or a point where I know a lot of things. So in terms of where I'm trying to find something, I'm trying to find the velocity coming out of this hole. So basically I want to know what the velocity at that point is. So I'm going to call that point 2. And then for point 1, I want to know as many things as possible. I'm going to want to know P1, Z1, V1. So basically I want to know, is there a point on this picture where I know the pressure, the Z value, and the velocity? And the answer to that is some point along this top. So some point here is going to be point 1. Now, as we saw in the last example, I don't have to worry too much about being on the same streamline, but in this case, I could do that. I could say there is a streamline. I don't know exactly where it is, but some point along this top eventually goes out that hole. So I'm picking whatever point 1 is, whatever that point is. Again, I don't really care in the horizontal distance where it is. I just care that it's somewhere on the top. So that's my point 1. So again, now I'm looking for V2. So to find V2, I need to know everything else in my equation: P1, P2, Z1, Z2, and V1. So again, I picked that point, point 1, because I knew all 3 of these things at that point. So in terms of pressure, this cup is obviously open to the atmosphere. So pressure at point 1 is atmospheric pressure. I can either call that atmospheric pressure of 101.3 kilopascals, or if I'm using gauge pressure, call it 0. In terms of my z's, I'm free to pick z equals 0 wherever I want, but then everything depends on that one location. So what I'm going to do, what I usually do, is pick z equals 0 to be the ground level. So I have z equals 0 down here. That means that z2 is going to be 15 centimeters. Means that z1 is going to be 30 centimeters. Now again, it doesn't actually matter where I pick this. I could have picked z equals 0 to be the top, in which case z1 would have been 0. If that's my new z0, that means z2 would have been negative 15. So again, be sure that down is negative, up is positive. So again, it doesn't matter where you pick them. Just as soon as you set that z equals 0 line, measure everything from there, and be careful with positives and negatives. So this is where I'm at so far. I want to know P2 as well. So I want to know what pressure at 2 is. Again, this is the external pressure, so whatever pressure outside of the fluid is, again, open to the atmosphere. So this guy as well is going to be atmospheric pressure. Then last thing you need to know is V1. So V1, what is my velocity of this point here? Key to this is that in the question I said I punched a small hole into the side. I have a small hole in the side. That means that water, although it's escaping, is not escaping very quickly in terms of volume. And so, because this area is so much bigger than my little tiny hole area, doesn't really matter how fast it's coming out here. This velocity is going to be really, really slow. So, in terms of my velocity V1, even though it's not technically 0, it's close enough. It's going to be small enough that it's not going to change my numbers very much when I plug it in there, being a really small number, so I'm just going to call it 0. So plugging all that information into Bernoulli's equation, I have atmospheric pressure, gamma Z1, 1/2 rho V1 squared, atmospheric pressure, gamma Z2, 1/2 rho V2 squared, atmospheric pressure, it's on both sides, get rid of it. V1 I'm calling 0, so we get rid of that as well. So now that those are gone, I can rearrange my equation. So 1/2 rho V2 squared. What I'm looking for is gamma Z1 minus gamma Z2, and then gamma is rho times G, so I can cancel my rho's. Solving for V2. V2 is 2G Z1 minus Z2. So 2, 9.81 meters per second squared. Z1, 0.3 meters. Z2, 0.15 meters. Gives me 1.71 meters per second as the velocity coming out of that hole. So last example for this lesson, I have a pitot tube. A pitot tube is basically this black thing, just a tube that's attached to a pressure gauge. And what you do is you stick it into some airflow, and what it does is it measures the pressure, and with that pressure you can figure out what the airflow is. So this is actually how planes know how fast they're going. They have a little pitot tube sticking out the front of them that measures the pressure difference, and that pressure difference is translated to a speed. So that's basically what we're trying to do here. I have this pitot tube in a wind tunnel, so velocity coming certain speed, and based on this pressure reading of 730 pascals, I want to know how fast is that air actually moving. So solving this guy, obviously going to use Bernoulli's equation again. P1 is gamma Z1, 1/2 rho V1 squared. It's the same thing at point 2. But again here, where is point 1, where is point 2? So again, where do I want to know things? Where do I know a lot of things? So in terms of my pitot tube, to measure the pressure difference, it's with a velocity. So I really want to know what the velocity is at the front of that pitot tube. So right here, that's going to be point 2. That's my velocity that I want to find to translate to pressure. Basically the pressure here at point 2 is going to be the same as whatever pressure I'm reading, so that's why I'm choosing that to be point 2. Then point 1, just somewhere up here, I have some velocity that I want to find, have some pressure that's again constant up there somewhere. Officially, what I'm actually doing is I'm going to make these along the same streamline. So just take a horizontal streamline, and that's officially where point 1 is. That way, Z1 and Z2 are going to go away. So getting rid of my two Z values, I'm looking for the pressure difference. Officially, what this guy's measuring is P2 minus P1, because I guess there's pressure P1 is kind of everywhere. It's kind of like atmospheric pressure, so it's not only there, it's down there as well. So this pressure gauge is really measuring P2 minus P1. That's what my 730 is. And then all I need to do now is on my velocities, so 1/2 rho v1 squared minus 1/2 rho v2 squared. Velocity v1 is what I'm trying to find. Question now is what's v2? So point 2, I picked this point because that's where I want to know the pressure, but also as the air comes in, there's already air inside of this, so air can't come in anymore because there's already air in there. So because there's already air in there, v2 is going to be 0. So I can get rid of that as well. Point 2 is a stagnation point. So rearranging this equation, I want to solve for my velocity v1. So P2 minus P1 times 2, divide by rho, take the square root. That is v1. Again, this P2 minus P1 is the 730 that was measured from the pitot tube. Density of air, not at STP, so because it's not at STP, you need to use the ideal gas law. So ideal gas law, density is pressure over constant times temperature. So my pressure here was 98,000 pascals. R value, 287 joules per kilogram Kelvin for air. And my temperature, 20 degrees Celsius, want that in Kelvin, so 293 Kelvin. Gives me a density of the air, 1.17 kilograms per cubic meter. Now it's a matter of plugging all those numbers to find my velocity. So again, plug the numbers in. 730 for my pressure difference, 1.17 for my density, gives me velocity 35.3 meters per second.